Okay, let's see. And don't take it as a challenge, take it more as a learning opportunity. Yeah. Folks online, can you hear me okay? Can you confirm? All good? Okay. Yep, so let's see. Thoya is here. Thoya is not here. She escaped. Rakshit. Ravi Shankar. They're all coming in. Huh? Ravi Shankar is here. Ravi Shankar, you're selected one. Need some time. Linton, come. Need more time. Then we'll give some time. Maybe take 5 minutes. Huh? No, the point is others. The point is everybody else needs to be there. Thoya, your name was selected. You're the first one. Thoya. Okay. I can play. Let's see. Let me see if your name is selected. Abu Bakr. You done? No? Abu Bakr, one more time. Karthik. Your name came. You can come with your system.
Any time to complete. Sorry, I did not get.
No problem. Let me do this instead of like this and we're offline. Yeah. Good. This is one. Choose to mirror. There you go. You're good to go. You don't have to join Teams. You can speak directly here.
Okay. So this is first part of the
But you need to share the screen also, no? So yeah, you have to be there on the Teams then.
I don't know why
Authenticator.
I'm not getting this mails.
Not mail. Authenticator app you have somewhere.
Maybe mail I should. No, phone I have not given.
Then do this. Just join on the web. Don't open up the Teams. Just join on the web.
Please. This. I can't use. One text.
You have to get the audio.
Audio is
Join now. You're good. Allow. Then unmute. People,
Can you hear me?
Yes.
Yes, sir.
Hello.
one of this has to be completely.
Yes, we can.
Hmm?
I will do it. Yes, we can.
Okay.
You can start.
Can you all see my screen?
Yes.
Okay. So the part one is data preparation and exploration. As part of this step, I'm loading and performing some initial analysis. So after running this code, so what are the observations? So the result output of this first part is this one. What are the total number of rows or data present in the data set? There are 1,338 entries and there are 7 columns. Okay, and the second part shows the column names and data type. And the third part shows count, mean, standard deviation, minimum and maximum. So I have explained this here. As part of this data set, so that data set has 1,338 records and there are no missing values in age, BMI, children or charges. So it means data quality is good. And the second part is with respect to average age. From the given data set, the average age is 39 years. The median age is 39 years, very close to the mean and roughly symmetric. Most people are between 27 and 51 years from the given data set. Age range is between 18 to 64. And conclusion is data. And when it comes to age, average age is, yeah, I've already explained this. So what is this from ML per se? Age has a wide and healthy spread, making it a useful predictor. And when it comes to body mass component, average BMI is 30.7 and median close to mean is slightly right skewed. And 50% of individuals have BMI between 26.3 and 34.7. So this reading, I'm taking this summary from this output. And from ML point of view, target is highly skewed. Linear regression may struggle with extreme values and it may require some scaling later point of time. I have not explored this point. Let me go ahead with this. Any questions from here? Okay. So the second part is data quality check, where I'm going to check missing values, duplicate. In case if duplicate exists, I'm going to drop it. And the third part is exploratory data analysis. So it is with relation between agent versus charges. I've done this. I've got this map where you have age on x-axis and charges on the y-axis. And if you look at the data points, it shows that charges are increasing with age. So I've noted down here the outcome, charges increase with age and relationship is moderately positive. So the second graph is between BMI and charges. And what is the important indicator or element of this is smokers. So what does it indicate? The blue dotted points and orange dotted points. Blue dotted points are smokers, orange dotted points are non-smokers. We have BMI on x-axis and charges on y-axis. You can see the blue dots are increasing with respect to BMI. So what does it indicate? Smokers show much higher costs. So high BMI plus smoker cost skyrockets, non-linear effect. For distribution of charges, this is a target variable. So we can see this graph, flatted charges versus count, distribution of medical charges. So it is rightly skewed. So the last part is 60,000. It shows few people have very high medical costs. Which one? This is charges. This count is here it is given. This number of people range actually. Distribution it is taken. The distribution of charges taken against the target variable. Next part is categorical analysis. Group by smoker and charges mean, and gender versus charges, and region versus charges. So this is the graph inside. Generally, as I said from the previous graph, smoker cost is 3 to 4 times higher.
Can you go back to that histogram? I had a question, right? So these are the number of bins that you're looking at. So
Range.
like when he hasn't specified, so can you go to the code a little bit? So SNS.histogram, right?
Yeah.
So that's taking a certain default value of the bins. Bins meaning like, you know, whatever your range is, I will divide that range in, let's say, 25 equal parts, right?
That is from the input data, the features.
Yeah. So let's say your medical cost was ranging between, can you go down your x-axis a little bit? So from 0 till further down. till $60,000 or $62,000. So it will take that range, and then I believe these are like 25, 30 bins, whatever is the default, right? So it's just chopping that interval into those number of bins, and it says, okay, how many of people are paying between $0 to $500? And that's the count that you're looking at. That's a typical histogram. Then the next bar, then the next bar, like, so that's how basically it's going.
But internally by default, it
You can
divides.
change
that,
that number of
yeah.
bits. In the, like the SNS histogram setting, you can change the number of bits. You can make it 10 also.
Okay.
So in fact, if you hover over it, you can find the help where you have written the SNS dot list up in the code, yeah. You just hover over that histogram, like the SNS dot histogram. If you just point your cursor there. Up, one line up, yeah, just hold it there, like in the line number 4.
Yeah.
05.
Line number 4. That's right. So it basically tells you now, right? So you can see all these options are there, common bins and the number of bins, where is exactly it is, anybody spotted that? Bins. So you can specify bins equal to 10, for example. Go ahead and write that after KD, put a comma.
Auto is there.
So auto, it will automatically decide.
Yeah.
So now in your code, go back. After KD, put a comma.
After 2 KD.
It doesn't matter. It's a function. No. After 2, sorry. After 2. Bins equal to 10 maybe. Let's redone this. You're already connected. If not, then your entire thing is going to be messed up. I don't think you're connected.
It's getting connected.
No, but you have to load up your data frame also.
Or the previous.
Okay, it has come. Never mind. So now you can see it has now reshaped your chart into the 10 minutes. You get that point? So just basically counting.
But initial value 100 it is.
So what it is counting is it's saying, so this is 10,000. So this bar is 10,000. So 0 to 5,000, 500 something people, 525, 530 people are paying that much amount of insurance, right? Okay, carry on.
In the next part of the code, I'm checking categorical values between smoker charges in a gender and region. So this is the result. And part 2 pre-processing, separating features and target. And here I'm checking identifying numerical and categorical columns. So we have age, BMI in children. Data type is object. Outliers here. So IBMI values are real medical cases. And we are not supposed to remove that. And feature scaling and encoding. This is pre-processing and pipeline. After that, I'm running the model building code and evaluation.
I don't think people are familiar with the pipeline. Can you explain? What are you doing in the pipeline?
Here, numeric pipeline and categorical pre-processing, I'm just setting it up in the background. It will run and instantiate it. The workflow actually.
Right. That's right. Yeah. So instead of doing one at a time, you're building a pipeline. So it will do all of those things. Now you come down to your next code. I think you have taken help from ChatGPT or something to write this code, right?
Both ChatGPT and Copilot.
Come down. Yeah, there. So you're saying model is nothing but your pipeline. Prep is going through the pre-processing pipeline that is defined earlier on, and LR is nothing but the linear regression. So pipeline is like a workflow, as Naveen was talking about. So it will first go through this object called prep, and prep is nothing but doing the pre-processor, which he has defined earlier on, right? The next thing in the pipeline will be LR. LR is nothing but the linear regression object that he's built. So instead of creating the instance, doing the data cleaning in a separate step, he has defined a pipeline where all the things will go through a certain data cleaning, and then he's fitting the linear regression. I would say, I mean, it's not necessarily required, but since the tool is writing that way, you should be able to understand. So that's where, I mean, that anytime you use the AI, you should understand what exactly it is doing. Right? So your understanding and your explanation part doesn't go away because AI is written the code. Carry on.
Next, I'm running the prediction and model evolution. So as model evolution, I am using MAE, mean average square, RMSE, R2. So these are the values I am getting. So the interpretation is mean absolute square. This is very reasonable given that medical costs can exceed $50,000. Root mean square as 2 observation. A few have very high cost cases and linear regression struggles with extreme values. As we have seen from the last graph, there is a right skewed 60,000 medical cost. That is right skewed. And the model R2 score is 0.8, that is 80% of the variance in medical insurance charges. Analysis and expected findings. So these are the features, interpretation from this code. Smoker strong predictor. That means this is the variable or column where we can correlate highly. And age is also a strong best fitted line. And BMI moderate, children weak, because here 635, if you look at the value, here children has lowest value. Anything is there from anything else? Any questions?
You show the correlation, like the
Coefficients.
place on down.
I've just answered here. What is the final conclusion?
Mm.
So linear regression provides a strong baseline for predicting medical insurance, but still it requires some scaling or further optimization. So we can consider it as a baseline, not the final one.
Okay. What do you guys think? Because he used the pipeline completely.
Automation.
He's used the pipeline. So where exactly you've done the prediction on the test data? Have you done the split of the test and train?
No.
You've not done the train test split. You should do it.
Yes.
Otherwise, it's like self-fulfilling. So,
No,
but
that-
work in your pipeline. Let's see. Even AI should not suggest that. Well, you have done that train test, no? You've done the train test. You've done the train test.
Yeah.
You've done that. So train test is done. So then you are invoking the pipeline, which is
At 20%.
You have done that, yeah. 80-20. And then come down, you're doing the prediction. A little bit up, up. There you go. So then you're doing the prediction on the test. So that is following that. The only thing that he has done is instead of looking at one step at a time for the missing values, outliers, and everything, that pipeline takes all of things together. Smoker is like, we have the smoker, yes, no. So those are converted into the 0 ones as we have done earlier. Yeah.
This is one.
So the graph, oh, like this one.
The coefficient will be able to understand that they are writing the charges and
Right.
are very correlated. But sure, like how you predicted that?
No, that's why it's drawn like this. So you can see this is no, right? And then what are you plotting here? BMI?
Yes, sir. No. This is the BMI. That is service. This is BMI.
This is BMI. This is BMI. So he's plotting. So you can see, look at this distribution, for example, which is no. Smoker is no. All of the orange dots are smoker is no, right? So you can see in this case, it's not that much linear as the BMI is going higher, right? And then you're looking at the charges. So what do you make out from the chart? Just by looking at the visible things, that non-smokers are paying a lot lower, right? Because all the blue dots are higher. For the same BMI level, there are some like non-smokers at the same BMI level who are paying high. But if you are 25 BMI, non-smokers are in orange, smokers are in blue. They're all higher, right? So you can tell me.
One or two cases. Or zero it is most important.
This is not the right one. So if you want to relate to it, then the way you should do it, you can have this as a box plot. So you can say the charges that I'm paying, right? This is, I mean, you've done the statistics. What type of chart is this? Scatter plot, univariate, bivariate, trivariate, multivariate.
Bivariate.
How many people thought bivariate? Raise your hand. It is a multivariate. You have three variables.
Smoking.
You have charges, you have BMI, you have smoker. So it's a multivariate chart, right? So anytime when you're looking into this, so the only flip side in the box plot will be, you can still do it, but I'll say probably you can have the, okay, just here. You can have your 0, 1 and then plot the charges. So my guess is when you plot that, you'll see that box plot for the smokers is a lot higher compared to the non-smokers. Yeah? Does that make sense? This is one way of doing it, not the right or wrong way. But good use of AI and fast turnaround.
I just wanted to jump into the conclusion that is whether it is best fitted for linear,
So you can jump to it.
linear regression.
Yes, yeah. So come to your conclusion then. Let's see what does the class think. Do you think it's a good model? Why or why not? How many of you think it's a good model? Go back to the statistics.
The accuracy score should be between 0.70 and 80, right? So
What is the accuracy? There is nothing called accuracy for linear.
in the
Hard to score.
No, come down to where your other half is from. Right over here.
Is good because R square is about 80%.
0.8 is correct.
0.7 to 0.8, 0.7 to 0.8.
so it comes, if it doesn't come within this range, so what we want in that case?
Choose a different model.
Okay.
We haven't spoken about what different models, but you can choose a decision tree, for example. You can use a support vector, you can choose a KNN, right? You choose many other techniques. You can choose ensemble. We'll cover all of them. So you saw the first day we were going really slow in terms of the AI. Second day also we were slightly sluggish. But once you get these conceptual underpinning, picking up a new model, building a new model doesn't take a whole lot of time, right? So today we'll just cover the linear logistics so that is very clear. From next time onwards, we'll squeeze more models. But linear regression is like a very, very simple model, right? So you can say, okay, if I don't even apply my brain, just throw it to the linear regression. Let's see what is the response we get, right? So R square is 80.69. Anyone who can tell me what does the R square mean?
This model explains 80% of variation of the target. For example, our target is price. So for some case, price is huge. For some case, price is moderate. For some case, price is low. So model is 80%. That variation model can explain why that some price is high, some price is moderate, some price is low. 80% of the time, model can explain that variation.
Yeah. So it's more about if you have built a model to explain what is happening in the insurance price, and you've got certain features that you're looking at. So how much of those features that you have in your model and the model that you built are explaining your label's performance? So it says 80% of what is happening in my label, which is nothing but your insurance cost, can be explained from this underlying equation that you have built, which is a decent model. And then your error is coming out to be $4,000, right? Now, you may have a fantastic R square, which is like, let's say 99%, but your error is coming out to be $10,000, right? So then you still don't have a good model. So you have to be looking at multiple things simultaneously. And that's where you know the model is good or not. So I'll say decent start, but not a great model. Yeah.
So even if R square is less, meaning independent variables does not explain the dependent variable.
Definitely.
If the error is also less, that means the model is good, but R square.
So you will not have that situation typically that your R square is bad and your error is really low. So that means, there is something wrong with the model. But if your R square is fantastic and yet your error is very high, then also something is wrong. So generally they will shape up in the same direction. But like I'll say, this R square, I wouldn't trust too much. This is the metric I'll be focusing on, error. But then I would like to try a decision tree and see, and we'll do that in the regression exercise. We'll build a decision tree and see whether we are able to lower the error. Then we'll do ensemble like a XGBoost or some other technique, and we'll see what error becomes there. So just hold on to this data. We'll do some further model on it down the road. One more person who can come in if you've done something really different.
So like I can come,
You've done something
I
different,
have not
mathematical
used- I have
derivations,
not used ChatGPT, so that is
Huh.
why I wanted to, so I am.
Come.
I did it.
but take not more than 5 minutes. And I will watch it. It's 2:35, 2:40, you have to wrap it up.
In this case, to the boss, we want him to get the funding from your. Within time. Yes.
We should have a timer. Okay.
Okay, so first, these are the
Can you share
imports.
screen?
Okay.
Please, so that others can also. And then you can mute yourself. Yeah, you're already muted, just share your screen. This one, yeah,
This one,
I think so, no?
this one is.
Yeah.
So first is, edit. So first, it is, okay, yeah. So first, these are all the columns, information, what and all columns we are using, then import, then I'm loading the data, and first 5 rows I'm able to, I'm seeing, and then info. Here I can see why info I check, because I wanted to see what and all categorical columns are there. If what and all numerical columns I am having, is there any missing data or not? All these things I can see. There are total 1,338 rows or records. There is no missing data. And there are 2 categorical columns. One is region, another one is smoker. So this information I got from here, and there is no null value or missing value. Shape I checked 1,338 of rows and 7 columns. And I already checked. I have not added the steps. There was one duplicate data, so I removed the duplicate value there. And in place 2 means it is directly updating the medical data, our data set, or our data, not data set, data frame. After that, I am having 2 categorical columns. So I'm changing that categorical columns to codes or numbers, because machine learning algorithm needs numerical value, the numerical value to work. And statistics also will not work on, or describe method will not work on categorical data. So for that, I'm converting all these columns, all these values to numerical values. Now, again, after that, I am checking the info. Now I can see there is no categorical value here. I am checking value counts for all the categorical values, because I wanted to check is there any duplicate thing or not. For example, here I am having one column called sex. Okay, so male and female. So in some cases there is like male, female, not male kind of things. That is data error. So to check, is there any that kind of misinformation, or that kind of bad data is there or not? For that, we need to check value counts. It actually tells under this categorical columns how many categories are there. Those categories are really meaningful. If meaningful, we'll keep them. If 2 categories are same, like male, female, not female. So not female and male both are same. So we can combine all those to male. So for that, I am use value counts. So I can see all the unique categories are there for all these categories. Smoker also there is smoke, yes, no, region and count. Now I am checking this describe. This is statistical information for age, sex, BMI, all these things. Count how many for age, how many counts are there. mean value, standard deviation, minimum value of age, 25% is like Q1. So we can say 25% of the cases or 25% of the patient, so 25% or below 25% patient having age of 27 in our data. So 50% median. So 50% people or 50% or below patient is having age 39. So same case 75 also same logic. Maximum age we are having in this data is 64. So like that, sex, BMI, children, smoker, for all we can interpret like that. So I'll come down. Here group by means here what I am checking for smoker. For non-smoker, what is the charges? For smoker, what is the charges? Like in SQL, how we do group by. So for sex also male, female, and for region, for which region, what is the cost for the insurance? Now I'll come to this hist plot. Here you can see this is not normal distribution. It is kind of right skewed distribution for age. It means here we can see most of the people who took the insurance is between 18 to like 25 kind of things. And there are few who has taken above 60. So this is the right skewed distribution. This is BMI. It looks like normal distribution, but it is not normal distribution. This is little bit right skewed distribution where we can see most of the cases BMI is from 28 to 35 kind of things in between in this case, in this range. And very few BMI is like above 50. Now here we can see this is heavily right skewed distribution for charges. Very few for very rare case charges are 60,000, or in rare case charges are more than 40,000, and most of the cases insurance charges are near to 8,000 to 10,000 kind of things here. All this I have explained below here. Now this is the box plot. We can see this is the box plot for age. This is the range 19, approximately 19 to 67 kind of things. This is the Q1 means 25. We can say approximately 25, approximately 20. Q1 is 25, and Q3 quarter three is 51 or 2. 39 we can see this is the median range. So here this is right skewed because median is near to median is near to Q1. If median is near to Q1, we can say this is the right skewed. Median is near to Q3, we can say this is the left skewed. So here median difference between Q3 to median is 13. Difference between median to Q1 is 11. So median is near to Q1. So this is the right skewed. So same thing I have done for BMI. We can same thing here. This is left skewed because median is near to Q3 here, and we can see some outliers here. This range is interquartile range. We can say this range above and below this range, whatever we'll see, that is considered outliers or extreme values. And below that, same thing. Here also we can see outliers. Now here I'm checking again the quartile 0, 1, 5, 95, 99, 1. So I already explained like below 50%, below 25% kind of things. So we can explain like that. This is statistical things. Now here what I did is outlier treatment. So we have seen a lot of outliers here. Here none of the distributions are normally distributed. That is why I have not used interquartile range. Here I have used capping and clipping, or clipping or capping, that one. So I have checked whatever value it is like 10% values, I'll be clipping inside 10% to 99%. So below
1%.
1%, yeah, 1% to 99%. So above 99%, whatever values will be there, it will be coming back to whatever value is there in 99%. And below 10% also, below 1%, whatever value will be there, it will be coming into 1% value. So I'm keeping all those values. Now, after that, I have checked the quantile this again. Describe method I have executed again. So if we compare old and new, we can see, we'll see the max value has been changed because I have removed the outlier using capping and clipping. So for example, so max value will not change. So here, here we can see charges. Okay, 63770, for example, maximum charges, and here we can see it is 48537. So yeah, maximum value has been changed here. So now here what I have done is correlation. So how the columns are related to each other. Okay, so what is the correlation between them? Why I have checked it? Because we are using linear regression. So before checking linear regression, we need to check, is there any multicollinearity or not? If there is any multicollinearity, we need to remove those multicollinearity, those columns, all those things. So this is the heat map. So using the heat map, I can see smoker and charges is having good correlation. This 0.79 means positivity correlation. Strong, we can say strong positive correlation we are having. Another thing is BMI and charges is having correlation. It is not strong. This is a weak correlation, but they are having correlation. Now, yes, if I come here now, so using this, we can see by using this, we can consider that two charges are very much influenced by smoker and BMI. Okay, so smoker is the column which can influence charges to highest smoker is having highest influence. Now there is no multicollinearity. Now here I did some scatter plot to check the linear relationship here. So here we can come smoker and charges. So we can see smoker is categorical value. So that is why 0 and 1. Why it is coming dot 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 dot? Because for 0 there are multiple smoker. For 1 also there is multiple smoker. But here what I am trying to show is for smoker, we can see the charges are below 4,000. It starts from 0, from 1 to, yeah, from non-smoker, it is 1 to below 440,000. But one smoker, it starts from near to 15,000 to 50,000. So we can see smoker, who are smoker need to pay more charges for the insurance. Who are not non-smoker can charge below. Less price for insurance. Now here I am just splitting. Now here I will start modeling my till that whatever I did is ADA, data analysis, all these things. Now here I am started modeling things. So first I am splitting X and I am just splitting X and Y. So I am just splitting X from where I am dropping charges, because charges is a target variable. So I'll remove that from our feature. And Y is our target. I am just keeping only charges here. Shape I am checking. This is the shape. Now why it is 6? Because I no 7. I have already removed one duplicate column. Now Y dot shape here. For Y there is only one thing, like it is not having any columns. So that is why it is having only rows. 1, 3, 3, 7 rows. And now if I Yes. So here I am doing standardization. So standard click scalar I am applying and fit transform I am applying here so that um, all the values for the features will be scaled between -3 to 3. Right, sir? Standard scalar. Yeah. So it will be on same range. Which value will be, if we don't do this, more value features is having more value can influence the model more. So we should keep all those value in similar range. That is why I have used standard scalar here. And now I just created or instance, I have created instance of linear regression model. Yes, linear regression model. Now here train test split I am doing. Here I am giving scaled X. So whatever this is the scaled X after scaling, I have given Y, which is a target. Test size means 0.2 means 20% of data I'll use for test, 80% of data I'll use for train. Random state 42 means it will not, because same code, if I same model, if I execute again and again, it will not influence, result will not influence change. So it will be like stable. So random state I have given here. After that, fit linear regression dot fit, I have given training data X train and Y train, because here I saved all these after 10 state train test split. I am saving all this data X train, X test, Y train, Y test. So X train and Y train I am giving because these are my training data. Using training data, I am fitting the model. Inside that, lot of things will happen, gradient descent and all those things, and model will here model will uh, um, estimate the coefficients and it will create a best fit line. So after this, it will predict. While predicting, I am giving X test because I need to pass the X test and I am getting the Y prediction. So, and here this should, I should run this before, but here after fitting means after training the model, this model will generate the intercept. It is a B0 and the coefficients like B1, B2, B3, all these things. So after training, when I train the model, after training, this will be the equation. The model with the linear regression model will, the linear regression model will create. This is the equation. This is the Y hat means prediction Y equal to this plus this into X1. This is the minus X2, X3. So this is the all the equations. Okay, so this is a linear equation. So now whenever new data will come, we'll be having X1, X2, X3, X3, X4, X6 kind of things. We just those value will add, and whatever value we'll get for new data, Y value will get. So that will be our new data. So that is your Y prediction. So same thing will happen in this line. So X test means all the X's we will be having. It will add, it will multiply X1, X2, X3 in these equations, and it will give the Y prediction. So now I'll come down. Here, what I did, I already told smoker has strongest. So by seeing this coefficient, we can see smoker is having strongest effect on Y because it is having correlation also, high correlation 0.79. And here also we can see 9251. This is the highest coefficient. It means by 1 unit increase of X5 or by 1 unit increase of smoker, Y means our price will be increased or influenced by 9251 unit. So this assumes smoker is statistically significant. Okay. Now I have created the error, mean squared error, mean absolute, and R score. So mean squared error, I have created, this is my 30. This is a mean squared error. It means on average about 5554 original units will take, means on average it will off, means our Y is off by 0.54 because this is the mean square error, same mean absolute error. And now last I have created R2 score. I got R2 score is 82%, means model can explain 82 cases why there is a variation of price in data set. There we can see there are a lot of, in many cases price are high, many cases price are very low, many cases price are moderate. So why some in some cases price are high, some cases price are moderate, some cases price are low. These things can explain 82% cases model can explain. So that much, sir. And the model is good because of that.
Awesome. Thank you. So you saw how typically we do. I mean, I can follow the same approach, and there is no difference in the model's performance, right? C only one type C. Might come in later on.
When you consider the real-time use cases where there are multiple target variables correlated, there are possibilities. In this case, the BMI and age might impact the insurance charges. So how do we analyze that? Whether it is still going good with the linear regression?
We'll do a different model, then we'll come back to it. Different set of model. In the linear regression, I mean, you can throw out one and see how's the model performance, right? Then you can bring in the other one, then see what is the model. So there's some trial and error that you will do. In interest of time, folks, I'll park the linear regression over here, then we'll move on to something different, right? I will not cover the lasso ridge because there is something that I haven't spoken about, which is the grid search. We'll be doing that maybe next time around. But let's read this article. I think I have given you this as the assignment. Article number 30. 30. And let me know once you've done that reading. Article number 30. No, classification matrix. We'll talk about this picture so that everybody understands. This is very, very vital, but very simple concept.
Again, and I'm telling they are saying GLM. What is GLM?
So it's a broad family of the generalized linear regression, linear models, right? So there are linear models, non-linear models, right? Non-parametric methods. So like logistic regression is also GLM. Lasso is a GLM. Ridge is a GLM. Linear regression is a GLM. So broader family of GLM, generalized linear models. So we'll look into this matrix. This is sort of like, we just spoke about the mean square error, root mean square error for the regression. Now we'll talk about the classification models and how do we assess the performance of the classification models, right? And then we'll take it from there. You'll build your logistic regression model, which is the classification model. Good. So this unnecessary. Just follow the same Titanic example that I showed you. Because if you let it write, it will write too much complex things. And like you spend like many hours, this will be understandable to you. Right. So you could define like
From this chart, you can see that what you mean, what we form the charts, right? Simple bilateral material. Stick to the fundamentals of the data. Know your grade, like that you can see. Because I mean, when I saw those X market, that's creating charts, which looks good, but then when you hit screen, then that's.
So there are many metrics mentioned over there, but just focus on this grid for a moment, and then we'll start talking about that. So ROC AUC we will not discuss. I mean, we'll discuss that maybe later on, but that's only for the binary classifications. Only for the binary, not for the multinomial classifications. Why don't we do this? Let me explain, and you can continue to read just in interest of time so that we can cover the logistic today as well. This is, very important concept, and this will help you a lot throughout your career, right? If you understand this now. But keep in mind the axis that I have modeled in my picture over here. When you do this in the sklearn, the axis will be flipped. The model will become the x-axis and the reality will become the y-axis. Don't get worried about that. It's very common, right? People are saying screen is not shared. And people are right. Should be visible. You're able to hear me okay, folks? Yeah?
Yes, sir.
Okay. I think I'm audible. Voice is breaking. That was at 2:06. Now, hopefully that is okay. Yep. So let's go on. So this is a classification problem. What is a classification problem? Who can remind the class? Hmm. Classification is instead of making the continuous variables prediction, you're predicting the classes, like who will buy, whether you are a buyer or not buyer, whether this person is going to survive, not survive based on the categorization. So categories, like, limited number of categories, right? Whether this person is going to respond to my offer or not, whether this person is going to default on the loan or not, right? So mostly it's binary. Mostly it's two classes, but it doesn't have to be two classes. It could be three classes also. It could be four classes also, right? Can you give an example where you've seen more than two classes in real world? Iris flows. Yeah. But in the other real world where you're, yeah. Give me example, like, where more than two classes are there. Two classes are very common. Grade system. Yeah, that's a good example. A, B, C, D, E. What is the likely grade the student is gonna get, right? Come. What else? Take Arpan's photo. He's the real star. No, seriously. Take his photo only. He's already setting his hair and everything right. So.
Smile, please. Good smile, please. Sir, please, in frame with the smile. Yeah. Thanks, sir. I'm taking some random photos. Please, sir.
Okay, fine. Yeah, so we talk any other examples of the categorical variables in reality?
Blood group.
Blood group, okay. How many blood groups exist? Blood test, yeah. Diabetic, non-diabetic, and pre-diabetic. Right, so you have three classes there. That's a good example. So when you go for the your blood report, they will say, you know, if it is less than 6, for example, then you are pre-diabetic. Then you're non-diabetic. If you're less than 6, HB1AC. I don't know. I don't know how many of you done the blood test, but if you ever do, then you'll know. So there's something called HbA1c or something like that. So if it is less than 6, then you are a pre-diabetic. Non-diabetic. If you're between 6 and 7, then you are a pre-diabetic. 6 and 7 is a pre-diabetic. And then if you're 7 and higher, then it is a diabetic. So it's a 3 classes classification, right? So we'll talk about the 3 classes later on, but for the simplicity, I'll stick with the 2 classes. What are the 2 classes? Cat and dog is what we're looking at. Is that clear? Now, who can explain me what are you seeing on the picture? Like on this thing right now? What does it tell you? Mm-hmm. Mm.
Whatever row we are getting,
Mm-hmm.
that is, that is actual, that is here, it is, for the true negative.
Hmm.
Row is actual. There are two categories.
True cat
Hmm.
direct value.
True negative is actually output maximum category with another category and evaluating the result. Here, y-axis is actual
Hmm.
and x-axis is the prediction, predicted.
Y-axis is actual or x-axis is actual? Yeah, that's right. So let's agree on few things first of all. So x-axis is the actual, and y-axis is predicted. So far with me, everyone?
Yeah.
How many animals do we have total? Total 100 animals. Why 200 you were saying? Who was saying 200?
Only the category.
No, not the category. Animal, total animals. Total animal, like types of animals are 2. But how many total animals? So let's say this is a room full of animals. There are 100 animals. Not you guys are animals. But yeah, but let's say I have cats and dogs in this room. Cats and dogs in this room, right? Then I'm building an object detection model. So I know how many cats and how many dogs I have let in this room. That knowledge I have. So I'm talking about that there are 100 animals in this room. And then out of those 100 animals, 70 are dog and 30 are cat. Is this clear, people? All the things which I'm writing or the arrows are there.
Yeah.
So far with me? Okay. Now let's come to the model part. Sorry, before we come to the model part. So the way you're going to read is reality will be read like this. So what does the reality says? You have to read in this way, in this color. And what is being the model's prediction will be in blue color. Is this clear? These 2 arrows? What the reality is versus what the model says, right? And this matrix is called confusion matrix, right? Why it's called confusion? Because all of us, we are confused. That's not the reason. The reason is model is confused along with us, right? But let's look into the actual axis. So let's account for all the animals that we have noticed there are there. So 70 dogs are there. Everybody agrees. So where are those 70 dogs? 60 here and 10 here. So we account for 70 dogs. Is that clear? Yes?
Yeah.
And how many cats? 5 cats, 25 cats, 30 cats, 30 cats. So if I'm working on this axis, I know in reality I have 30 cats and I have 70 dogs and all the cats and all the dogs are accounted for. Correct? Now, what is it that the model is saying? How many model is saying I have identified the cats for you? Can anyone tell? 35 cats. Right? So the model says 25 plus 10, 35 cats I have found for you. And how many dogs? 65. 65 dogs. So if I add up 65 dogs and 35 cats, how many animals? 100 animals. Everybody's accounted for, but model is making wrong prediction in certain cases, right? So there are no 35 cats. There is only 30 cats, right? And there is 70 dogs. So 5 dogs just went missing. So 5 dogs got misclassified as cats, right? And there is further misclassification as well. So now let's look into the true positive, false positive, true negative, false negative as well, right? So let's say the positive was that I built this engine to detect a dog, right? So let's say when you are building an engine to see who's going to respond to your offer, the responder will be a positive class. Non-responder will be a negative class, right? So the dog will be a positive class and the cat will be a negative class. Why? Because I've just defined the problem like that I want to identify a dog. So dog is a positive class. Automatically the cat becomes a negative class. It works only in the binary. If you have more than 2 classes, then positive and negative sort of like loses its significance there. But let's say the dog is positive, cat is negative. So model says I have identified a dog and in reality it is a dog. So this is nothing but your true positive. True positive meaning model says dog. In reality, I know it's a dog. Model is right. It's a true positive identification. This is the correct classification. The model did work as expected. Is this clear? Quadrant 1. Quadrant 2 is this. What does the model say? I have identified a cat for you. And in reality also, it's a cat. How many times that is the case? 25 times. So 25 cats have been correctly identified by the model and 60 dogs have been correctly identified by the model and rest are incorrect, right? So let's look into this one. So this is true positive, or sorry, true negative and true positive. Now let's look into the false negative. What is a false negative? That the model says it's a negative, but it's not a negative. It's a false negative. So the model says it's a cat, but they're not cat, they're dog, right? So 10 cats or 10 dogs have been misclassified as cats. Is that clear? So that's why it's a false negative right over here. Similarly, in this case, what does the model says? I have identified a dog, but in reality they are cat. So 5 cats have been misclassified as a dog because it's a computer vision engine that we built, right? So it looks into a small dog and gets confused and says it's a cat, and vice versa. The cat could be really humongous as well, right? And it will be getting classified as a dog. So it gets confused basically, right? So you can see these are the wrong classifications. The quadrant 3 and quadrant 4. So out of the total animals, how many are correctly classified? 85. So your accuracy is nothing but this number divided by 100. So you are 85% accurate, your model, right? The accuracy of the model is 85%. Is this clear so far?
That's a cat only. We are clear over here. There also false cat, false negative is a problem. That is clear. Why are we putting it like this?
Anybody? Why are we doing this?
We can understand where
Hmm?
the
Hmm. Hmm. Yeah. That's right. That's right. So, I mean, the model gets confused, right? So in reality, the model gets confused in anything. So let's say when we're going to do the Titanic, what you'll be doing is you'll be giving your train, X train, Y train to the model and say, okay, go learn that behavior. Who's going to survive? Who's not going to survive, right? So the model learned that behavior, that this person is going to survive. This person is not going to survive. Then you'll give it a brand new data, the X test that you've held out. And you'll say, make your prediction. Who do you think is surviving or not surviving? So model will say this person is going to survive. This person is not going to survive. Against that, I will know who really survived, who did not survive to really ascertain the model performance. So this is the one of the most robust and most popular way of assessing a classification model. Something similar to the mean square error, right? You got the actual error. You got the actual house price, but still you're making a prediction and then you're computing the error. to know how the model is performing, right? Same thing. I know who's a dog, who's a cat. Then why I'm asking the model to do it? Because I want to know whether model has learned that behavior or not, right? So once I know that model is able to do a reasonably good job, then I will release that model in the production, right? Any other questions so far? Now, huh? Hmm. Hmm. Because you have to account for the entire universe of the sample that you're looking at, right? So you're making, the model is making a prediction on 100 samples. Hmm. 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 You can do both classes. You can do the accuracy of the positive, accuracy of the negative, and overall accuracy. You can do all three of them. When we do a confusion matrix in sklearn, you will see all numbers will come in there, right? But that's a great question. Shall I move on then? This is going to confuse a lot of people. So is this clear so far with me? Okay. So now we will go into something called as a precision, right? And precision works on model's prediction axis. This is the axis that you have to look into the precision, which is not the same as accuracy. So these three numbers are very different number. Precision, recall, and accuracy are three very, very different numbers. So do not get confused and do not throw accuracy as a term to say for the precision and recall and all of that. Precision and recall is something that we use very heavily in the Gen AI as well. Like, how many of those words or catchphrases are really done correctly versus how many of those recalled correctly. We'll talk about that. So precision works on the model's axis, right? So when model says that I have identified a cat, how many times the model is right? That's how basically the plain English interpretation is. When your model says, I have got a cat identified for you, how many times the model is right? So who can tell me the math for the precision? Yeah, so precision for the cat is 25 divided by 25 plus 10. Is this math clear? Precision. So model says I've identified a cat for you. How many times it's saying? 35 times it says I have got a cat for you. How many times the model is really right? 25 divided by 35, and that's the precision for the cat. So when your model says I have got something identified for you, it is right only precision times. Basically, the precision number that you're looking at is the rightness or the correctness of the model. Who can tell me the precision for the dog? 60 by 65. 92%, right? So is this clear also? So the model says I have identified a dog for you. How many times? 5 plus 60. 65, but model is right 60 times out of 65. So the precision for the dog is 60 by 65. All good? Now let's do the recall. Recall is working from the reality axis. This color, orange color, dark orange color. This is the axis the recall is working from. Recall says out of the total cats that I have, how many were correctly detected by the model? Total cats, total dogs, how many of those were correctly detected, right? It's a detection rate. So how many total cats are there? 30. Total cats are 30. How many are correctly detected? So the recall for the cat is 25 divided by 30. 25 divided by 30. Hmm.
Model is identified 25 correct.
Hmm.
So the amount of time the model is correct is 25 divided by 30 or 25 divided.
No, 30 only. So recall is saying in the real world, how many cats are there? What is the answer? 30. Then how many of those 30 cats have been detected or identified by the model correctly? That is 25. So the recall for the cat is recall meaning how many of you can recall, right? So how many from the overall universe you're able to recall? So that is 25 divided by 30. Recall for the cat. Recall for the dog. How many total dogs are there? 70. How many are correctly recalled? 60. There you go, right? So you have done the entire math, and there is a, like, I'll show you the confusion matrix, which basically talks about that. So precision for cat, precision for dog. Where did we define that? Here. Recall for cat, recall for dog, accuracy for cat, accuracy for dog, and overall accuracy. So these are a bunch of metrics that we generate in a confusion matrix, right? Now, why do we need all of them? Why not just work with the accuracy?
Based on the business setup, so the modeling as we told, medical field, if some person is having cancer or some disease, if I identify as that the patient doesn't have that particular disease, he will not go to any other tests or anything. So he will assume that I don't have that disease. That is critical thing. So in that case, recall is important because false negative, that is critical in the case of medical science. But for example, another is for precision. Mail spam and ham detection. So if I am detecting any mails which is not spam, but it is my model detected as a spam, that is false positive. In that case, we can use precision.
Okay. I will tell you the reason, which is sort of like building on what you've explained. The accuracy number is not robust for something called as imbalanced data, right? So you should not rely on the accuracy number for unbalanced data or imbalanced data, how we want to say that. So what is an unbalanced data? When something is happening, let's say 99% of the time, and the other event is happening only 1% of the time. Yes, like in any fraud cases, non-fraud will be 99% of the time. Most of the transactions are not fraudulent. Like let's say the credit card transactions, right? Only 1% of the transactions will be fraudulent, right? So this is a fraud. Still, I mean, you will not be able to fix that completely. So let's say I do not build any model at all. And I say all my transactions are non-fraud. What is going to be the accuracy? Without building any model, I'll say all my transactions are non-fraud. I will still be 99% accurate, right? Because we are saying that 99% of the transactions are non-fraud. So without building any model, I can say all my transactions are non-fraudulent. Let everything go through and classify that as a non-fraud. And we are still 99% accurate. Very, very good model. Awesome model. Accurate. But recall is 0. Why the recall is 0? Yeah, because these 1% of the fraud cases, I'm not able to detect any of the fraud cases, right? So remember, the recall works from the detection axis. Like, in reality, how many fraud cases are there? So your model is really bad in the recall. Like, it's not able to detect any fraudulent cases. So if you're not able to detect the fraudulent cases, then why do you have a model at all, right? So it's not a good model at all, right? So from accuracy, when you look at it, it looks like a fantastic model. But the moment you look from the recall, it's a very, very bad model. It's like, no model at all. So that's why it's very important that you look into all of these metrics together, right? And in error terms, when we're looking at the regression, we were saying error should be low. How should these metrics be? Any idea? What do you think these metrics should be? High or low? Okay. So in a good looking model, your accuracy will be approaching 1 or 100%. Your precision will be approaching 100%. Your recall will be approaching 100%, right? So that means whenever your model does any classification, let's say again, we are looking at this 2x2 matrix, right? So this is the, I'm going to flip it now. So I'll say this is reality. And this is model performance, right? So I want, and let's say this is 0, 1, and this is 0, 1. So I want all my observation to be sitting in over here and all my observations to be sitting in over here. So there's no misclassification, right? There's nothing there. So 100% accurate. And when my model says I've identified 0, all of the cases are really 0 in reality. When the model says that from the reality axis, again, it's able to detect all of them. So ideally, they should be all very high, but in reality, it doesn't happen. It should not happen also, right? Now, let me just quickly show you one real confusion matrix, and then we'll take a break at around 3:30 to avoid the crowd. And there is a F score as well, right? So for example, you can see over here now, right? Same thing we have done earlier. But now we are looking at, and you don't have to compute by hand. Arpan may still continue to compute by hand later on. I don't trust the system, huh? So, but you don't have to compute by hand. So this is completely done by the classification report, right? So you have 0 and you have 1. And you have a precision for 0, you have a precision for 1. You have a recall for 0, you have a recall for 1, right? You have an overall precision. You have an F1 score. I haven't spoken about that, but I'll explain that. And then you have a support. And then you have the overall accuracy number over here, right? Support is the number of observations. So how many zeros are there? Number of observation. So how many zeros are there? 13170. How many ones are there? 444. How many total observation? Summation of these two. Clear? Just the way they have defined the function, right? So let's see. So accuracy is 80%. Accuracy not looking too bad. Who can tell me the interpretation of 86 now? Let's change it to not cat, but let's change it to non-defaulter and defaulter. Yeah, now tell me.
As a non-defaulter, my model correctly predicted 80% of the time as a non-defaulter. 86. Sorry, 80% of the time. It was a non-defaulter.
How many percent?
14%
14% chance of the error. Yeah. That's exactly right. That's exactly right. So it says when your model says this person is gonna be non-defaulter. You built a model for doing the prediction of who will default, who will not default. And the model says this person is gonna be a non-defaulter. 86% of the time, model is right. 14% of the time, model will be wrong. Right? So there will be 14% of the actual defaulters being classified as a non-defaulter, like in terms of the true negative, false positive, and all that matrix, right? So that's one number. Who can interpret this one?
predicts for that 62% of the time our model is correct prediction and
Yeah, so when your model has predicted a defaulter, 62% of the time the model is right. And 38% of the time your model is wrong. So this is not a great model because even if I don't build a model, I can say 50-50 odds that you'll be a defaulter, non-defaulter, right? So like, I'm not getting a true lift, right? So this number doesn't look too good for the defaulter identification. So there is only 62% who will be the true defaulter, but remaining 38% are the non-defaulter. So these are the people I should be writing a loan to. But because of my model, I'm not giving them a loan because they have been falsely classified as a defaulter, right? So now you can see every number has a significance associated with this, right? And what is this? This is the average, right? And then there is, when you look into the actual classification report, you will also, so there is one called the arithmetic average, and there's one metric which is the weighted average. You guys are aware of the weighted average? No? Weighted average will be basically you have to say the overall number will be 0.86 times 1317 plus 0.62 times 444 divided by 1761. That's the weighted average math, right? So instead of just doing the arithmetic average, which is take 0.86 and take 0.62 divide by 2, I'm also paying attention to how many times each sample is represented. So 86% precision is for 1317 samples. 62% precision is for 444 samples. And that is going to give me a different number, which is going to be accounting for the weighted average, right?
So you give that pricing.
Right. Yeah, I have a puzzle later on, then I can ask if time permits, but weighted average very important. Now let's do the recall very quickly. What does this mean? 88%. Non-defaulter. This is ND.
88% of time my model correctly predict that.
No, not. So from the overall, so let's say in my overall universe, I had 100 non-defaulters. 88 non-defaulters have been correctly detected by the model. 14 non-defaulters are not detected. So they means they have been sent in the defaulter category, right? 12, sorry, 12. 58%. Yeah, that's right. So 50, so that means from the overall universe of the defaulters, only 58% is your detection rate. 42% are going undetected by your model, right? So that means that there is a huge gap for detecting the true defaulters in your model. So this is not a good model at all, right? Because there's a lot of gaps in your model performance. So even though if I look at the accuracy number, I'll say 80% accurate. I mean, what else are you going to ask, right? I mean, this is a fantastic model. But when you start to look into from the precision, from the recall lenses, then picture become more clear that this is not a good model after all, right? So that's where this really comes in. And precision and recall can be optimized. So there are cases where recall is important. There are cases where precision is important, right? And there is cases when both are important. So that's why we have something called as a F score, which is nothing but a harmonic mean. Arpan, what is the definition of harmonic mean? Arithmetic mean, geometrical mean, harmonic mean. Hmm? Who can look up quickly and tell me? So it's basically 2 times precision plus recall divided by P plus R, but you can confirm if I remember correctly. This is the harmonic mean, right? So if you take this precision number, this recall number, and do this math, you will get this F score, which is, huh? Sorry, 1 by P plus 1 by R. Okay. Huh? Let's see. I'll just pop it up. Harmonic mean.
No, it's 2 into precision into recall, by precision plus recall. That is correct.
Yeah, this is the one, right? So you can see these are the 3 different means. 2 times AB divided by A plus B, right? So that's what I had there originally, which is the correct one, not the 1 plus, but the P plus R only, right? So it's just basically a good balance between the precision and the recall. And when we come back, we will start over here again, right? And we'll do a logistic regression, and then we'll do the exercise, and we'll continue from there. So let's take a quick 10-minute. So we should be back by 3:45, yeah?